Now let's have a look at the concept of multiway tree, which is actually an extension to the previous radix search tree approach. So remember that in the case of radix search trees, the height of the tree is limited by the number of bits in the keys. So we had, for example, B bits to represent the values, the codes. Therefore, the largest depth could be 5 in that example, not larger than that. It will be B in general. Now, if you have larger keys, then the height will increase. Now, if the height increase, we know we have to do more comparisons and we will have to do more jumps, which takes time. So we would like to also keep the height under control. So we want larger bits, but not deep trees. So one way to overcome this would be by making use of the multiway radix tree approach. So the branching this time is not done bit by bit, but now we consider several bits. Typically 2, but it could be more. So in general, say if we're comparing m bits at once, then the search will speed up by a factor of 2 to the m. Because if you're looking at m bits, you have 2 to the m possible outcomes. So you have 2 to the m possible children going out of that node. So you will take one and ignore all the rest. Therefore, it will be a significant improvement because you're throwing out 2 to the m minus one of those possible subsets and taking only one subset where you're searching for the element. So that's a significant improvement. But the problem is if you are using m bits, as I said, you have 2 to the m different children. Therefore, you need 2 to the m separate links pointing to those children. And in most cases, most of those links will actually be null pointers. And then you will just be wasting space. So there is too much waste of space, unfortunately, in this approach. So we need a solution for that we'll discuss. So here's the example. Again, we have codes like T, for example, corresponds to 10100. We want to insert it into this tree. But before inserting T into the tree, let's see how the tree is. Note that from the root, this time our m value here is 2. So I'm comparing the leftmost 2 bits rather than the leftmost bit. So the possible outcomes are 0, 0, 1, 0, 1, 1, 0, and 1, 1. So therefore, from the root, I have 4 outgoing links to 4 different children. Now, for the case of x, it's the only element there, so x is just a simple external node. However, for the others, I have internal nodes. Like A, C, E, G have common leftmost 2 bits. They're all 0, 0, starting with 0, 0. So after 0, 0, they're differentiating. Therefore, they're all under here. For the case of, for example, H, I, L, M, and N, for these 5 keys, they have the same 0, 1 prefix. So the leftmost bits are 0, 1. But H and I have 2 more common bits. L and M have 2 more common bits among themselves. But the common bits here are different than the common bits here. It's 0, 0 for these, and this is 1, 0. Remember, the order was 0, 0, 0, 1, 1, 0, and 1, 1. Therefore, H and I start with 0, 1, 0, 0, whereas L and M start with 0, 1, 1, 0. And N starts with 0, 1, 1, 1. Now note that actually this internal node, and the null pointers here, they're all at the same level. It's just drawn this way because it's difficult to fit all of them at the same level. Similarly, for the case here, P, R, and S, and later when we insert T, they all have common leftmost 2 bits, 1, 0. But for the case of P, it will be 1, 0, 0, 0. For the case of R and S, it will be 1, 0, 0, 1. For the case of T, for example, it will be 1, 0, 1, 0. Really, if you look at the code here, you will see it's 1, 0, 1, 0. We don't look at the fifth bit. We don't need the differentiation there. Looking at the first 4 bits was sufficient for us. So this is how the M-way radix searching works. However, as we said, there is too much wasted space because when you go back to this graph, you see that there may, for example, null pointers. You have links there, but the links are empty. They just have null value in it. So there will be a lot of unused links, null links. So there's too much wasted space. And this waste gets worse if M gets larger. However, if M gets larger, actually, this tree gets wider. Now you have same number of elements. So if the tree gets wider, it will also be more shallow. The depth will decrease, which is something I like. So if you have to store all those elements in the tree, if you make the tree narrow, it has to be deep. And when it becomes deep, you have to do many jumps to reach the results, the leaves. If you make the tree wider, then the tree doesn't have to be that deep. So you will end up with a shallow but wide tree. So it is nice to have a large M value in terms of the depth. However, to achieve this, then we are introducing wasted space. So there's a trade-off there. The runtime will be log base, this time not base 2, but it is log base M of N. So the regular search trees, digital search trees, were a special case of the the regular radix search tree is a special case of the multiway radix tree. So as M gets larger, really it becomes feasible in terms of runtime, but in terms of memory usage, it gets worse. Therefore, we need a hybrid method where at the top we have large M so that I have smaller islands below. Okay, so at the top, remember the leftmost bits for most of the elements will be similar. So if you make M large at the top, you can just get smaller islands or groups of elements, and then for the lower ones, for the lower levels, you may make M smaller. So you don't have a constant M value. Typically, you have 2 different M values.